A cylinder of ferromagnetic material is 6 centimeters long and 1.25 centimeters in diameter. And so this is the diameter, this is the length, and has a magnetic moment of 7.45 10 to 3 EMU. Find the magnetization of the material. So this is part A. I have a cylinder of ferromagnetic material, and I know that the volume of the cylinder will be equal to pi r square h, where h, the length, is 6 centimeters, and r, the radius, is 1.25 centimeters divided by 2. So if I calculate the volume V, this will be equal to pi 1.25 divided by 2 square times 6. So that's roughly 7.36 centimeter cube. Now the magnetization is magnetic moment per volume, and it's the same in CGS or SI. So this is going to be equal to the total magnetic moment, 7.45 10 to 3 EMU, divided by the volume. The volume is 7.36 centimeter cube. So I find that the magnetization is 1012.2 EMU per centimeter cube. So this is roughly the magnetization of this ferromagnetic cylinder. What current would have to be passed through a coil of 200 turns, 6 centimeter long and 1.25 centimeter in diameter, to produce the same magnetic moment? So I have these coils with n turns, where n is the number of turns is 200, and I would like to know the magnetic moment this will create, and the magnetic moment that is created by n current loops will be equal to n times current times area. And notice that this is the SI, this is an SI, so I have to convert the area to meters square. So this is 200 times the current times the area, pi 1.25 over 2 square, and since this will be centimeter square, it's 10 to minus 4 meter square. So this, the current is in amperes here. So this will be equal to 2.45 times 10 to minus 2 I in ampere meter square, and I know the magnetic moment in EMU. Now, how do I convert between ampere meter square and EMU? Well, I know that a magnetization of 1 EMU per centimeter cube is equal to 1000 ampere per meter. So this implies that if I multiply this by 1 centimeter cube, 1 EMU is equal to 1000 times 10 to minus 6 ampere meter square. So this will be 10 to minus 3 ampere meter square. So 1 ampere meter square is 1000 EMU. So this is the conversion between magnetic moments. Now I have 2.45 10 to minus 2 I in ampere meter square. So this will be the magnetic moment is 2.45 times 10 to minus 2 I in ampere meter square. If you convert this to EMU, 1 ampere meter square is 1000 EMU, so this will be 2.45 times 10 to minus 2I. 1 ampere meter square, 1000 EMU, so this will be equal to 24.5 I in EMU. The current is still in amps here, so I can find that the current should be since the magnetic moment I'm looking for is 7.45 10 to 3 EMU, so I can see that this should be equal to 7.45 10 to 3 EMU. So the current must be 7.45 10 to 3 divided by 24.5, and I find that the current I would need would be roughly 304.1 amps. So I would need a huge current to obtain this effect in a 200 turn coil. So using this ferromagnetic material is really a good choice to produce this magnetic moment. If a more reasonable current of 1.5 ampere is passed through this coil, what is the resulting magnetic moment? So this is basically unreasonable current. It would basically burn the coil probably, so you cannot really pass this much current easily without a lot of cooling. Now if I do the same thing with a 1.5 amps current, this is 200 turns, 1.5 amps, pi 1.25 over 2 square 10 to minus 4, that's the area. This gives us 3.68 times 10 to minus 2 ampere meter square, which is 36.8 EMU. So we would find that a more reasonable current of 1.5 amps would produce 36.8 EMU as compared to 7.45 10 to 3 EMU. So there is a huge advantage in using this ferromagnetic material in the cylinder. Okay, so we talked about a cylinder of ferromagnetic material, 6 centimeters long, 1.25 centimeters in diameter, with a total magnetic moment 7.45 10 to 3 EMU. Magnetization is magnetic moment per volume, so I calculated the volume from pi r square h, where r is the diameter divided by 2, and the magnetic moment is in EMU, volume is in centimeter cube. I get the magnetization in EMU per centimeter cube. For part B, instead of using this ferromagnetic material, I wanted to obtain the same magnetic moment using coils with 200 turns, carrying a current I with the same radius, and this gives me basically the magnetic moment equals NIA. This is an SI equation, remember. The magnetic moment is pole strength times the distance between the poles in CGS. So we're using SI units here. So this will give me 2.45 10 to minus 2I in ampere meter square. I have to know the conversion between CGS and SI. 1 EMU per centimeter cube is 1000 ampere per meter. So this is for magnetization. And you can see that if you multiply both sides with 1 centimeter cube, that is 10 to minus 6 meter cube, you obtain 1 EMU equals 10 to minus 3 ampere meter square, or 1 ampere meter square is 1000 EMU. So this is now magnetic moment conversion. So if you substitute here for the magnetic moment 2.45 10 to minus 2I, that is 24.5 I in EMU, when we convert from ampere per meter square, and this should be 7.45 10 to 3. That requires a 300 more than 300 amps of current, which is unreasonable. If we substitute 1.5 amps, which is a more reasonable current, we find that the magnetic moment we would obtain would just be 36.8 EMU.